Thanks for the introduction and good morning. Yeah. So they will just be talking about some quantum algorithms for solving non-unitary dynamics, and then the approach is really based on relating the general non-unitary dynamics or the ordinary differential equation with the Hamiltonian simulation problem. So this is a joint work with Jinpeng Liu and Lin, who are both sitting in the audience, and here's the archive number of the paper. So I would just start with some introduction of the Hamiltonian simulation, and also I want to just give you some motivation on why we really care about quantum algorithms beyond Hamiltonian simulation as for non-unitary dynamics, and then we'll just go into the details of our algorithm. Okay, so I guess many of you are really familiar with the Hamiltonian simulation, but here's a really high-level overview. That is for the Hamiltonian simulation. So basically, we would like to simulate this Schrödinger equation with, in general, with a time-dependent Hamiltonian h of t. So here, h of t is a Hermitian value matrix function, and then for this Hamiltonian simulation, since the quantum devices is based on some quantum mechanics stuff. So basically, this is Hamiltonian simulation problem is quite natural for the application of quantum computers. So we have so many efficient Hamiltonian simulation algorithms. So here I just list a few of them, including the Trotter method, the quantum walk, truncated Dyson, and QSP, QSVT, so on and so forth. So basically, we have lots of efficient Hamiltonian simulation algorithms for both time-independent Hamiltonian as well as for time-dependent Hamiltonian. But today's talk will be about something beyond this. That is, we would like to focus on some non-unitary dynamics. So basically, still focus on some ordinary differential equation, but the evolution operator is not necessarily unitary. So at the first, I would just want to show you some motivation of why do we really care about this non-unitary dynamics. So basically, from my point of view, I just feel there might be two main reasons. So the first reason is that for many non-unitary dynamics, so they are very hard for classical devices. So for example, starting from the general differential equation, basically you can just see many applications in different subjects. But the thing that I want to highlight is that so for many practical differential equations, so they are naturally in high dimension, which means that so if we want to use classical computers to solve this general differential equations, then basically we will suffer from a large number of degree of freedom. So that probably will introduce a lot of computational overhead. And of course, so probably you have already heard about the curse of dimensionality in some kind of high dimensional partial differential equation. That is if the spatial variable, if the dimension of the spatial variable is very high, then even if you just discretize each dimension with a few basis function, then the overall degree of freedom will also will grow exponentially in terms of the dimension of your spatial variable. So basically means that for classical computing, so probably we have to pay a lot of price. So this is and then we know that the quantum devices can possibly achieve some speed up in terms of the dimension. So this is why we like to explore whether quantum devices can also be useful for maybe the general differential equations, the high dimensional differential equations, even beyond Hamiltonian simulation. So this is probably the first reason. And the second reason is really that so there are many applications of the general non-unitary non-unitary differential equations. And then here I just have a very rough list, but I'm going to show you three concrete examples that I found might be interesting. So the first example is it is still some quantum dynamics, but not the closed system quantum dynamics. So we just want to consider the open quantum dynamics. So the open quantum dynamics really means that so since we kind of studying the system in a maybe in a large or even in an infinite space or alternatively probably we would just want to consider the dynamics in some finite box, but we have some bath, we have some environment where your system, your active system and the bath can interact with each other, and these types of the open quantum dynamics has many applications, including the molecular scattering, the photo dissociation, and nanotransport, so on and so forth. But the point is that so since we have the we may have the environment or we may have the full system. So if we only care about the dynamics within this finite box, then basically the evolution operator within this finite box is no longer unitary because it will be affected by the other parts of your system. And to deal with this, so basically one there are actually many different approaches, and one useful approach is based on the complex absorbing potential method. So the complex absorbing potential method is trying to use an additional term to model the effect of your full system of the environment. So basically, for example, if we look at this Schrodinger equation, we have the standard Hamiltonian part, which is the Laplacian plus the potential. So this is the standard closed Hamiltonian part. However, if we also want to model the effect of the general system or the other parts, and then so we will add a additional potential, which is called the absorbing potential, and you can make this to be a diagonal thing. But the point is that, so here we have some imaginary unit in front of this potential, which means that if we look at the entire matrix, then it is not a Hermitian matrix. So in the literature, it is also called the non-Hermitian Hamiltonian, which really means that we have this kind of general matrix, and now the matrix is general, so the evolution operator is no longer unitary. Okay, so this is probably first application that I want to mention, and the second application is from the partial differential equation. It's just the convection diffusion equation or vection diffusion equation. So basically, it's just a model for some fluid or some many physical systems. So basically, we would consider this partial differential equation, and we want to include both the diffusion term, which corresponds to this Laplacian operator, and we want to include a convection term, which is this gradient or the divergence operator, and maybe we will have some kind of external source, like your heat source or whatever source that we want. So if we look at this partial differential equation, then of course, for partial differential equations on quantum devices, so typically we will just first do the spatial discretization and transform this into an ordinary differential equation and then apply our ODE quantum algorithms. But after the spatial discretization, we can see that, so now we have the Laplacian term, we have this gradient term. So basically, one of them will correspond to the Hermitian part, another will correspond to the anti-Hermitian part. So in general, this matrix is not just a Hermitian or anti-Hermitian matrix. Yeah. I think I have a question online, right?
Oh, hey. I wanted to ask, isn't U a scalar? How are you taking the divergence of U?
Oh, here, this U here is a scalar. And then, after the spatial discretization, U will be a vector. But, in the partial differential equation, so here U is just a scalar. Okay, is that okay? Or
I guess it's okay.
Okay, yeah, I guess it's okay. Okay, I will just go ahead. Yeah, so, this is my first time to see this system works. It's really efficient. Yeah. Okay, great. Yeah, so this is and yeah, of course, I forgot to mention that if you have any questions, just feel free to interrupt me, and I will be very happy to take that. Okay, so this is the second example, and the third example that I just recently added to this slides is that, so it's from the optimization, that is if we want to consider the gradient flow of the dynamics. That is, in the optimization problem, so basically we would like to, this is really, preliminary introduction, that is, we want to for example, minimize the objective function f of x, and then probably the simplest method would be with considering the gradient descent method, that is we just update our current point by the negative of the gradient, and then actually in the continuous formalism, so this can be reformulated as the gradient flow. That is, for example, if we take the learning rate or the step size goes to 0, and then probably we can just formulate this as this ordinary differential equation dx dt equal to the negative of the gradient of my function, and then yeah, this is another example of the optimization, and I think my collaborator Jinpeng has another work on using this gradient flow for optimization, but in that work it's kind of more general for the nonlinear differential equation, but this is probably the third application of the general differential equation. Okay, I hope I have given you.
Sorry for those three types of different problems. Can you say more about how large the dimension could be?
Yeah, okay, yeah, that would be a great point. So actually for all of the three types of the equation, so first of course, for the quantum dynamics, so basically we probably have some many-body system, and then the dimension will be extremely high. And then for the convection diffusion equation, so this is because this is a partial differential equation, if the spatial dimension is very large, then after spatial discretization, then it can be the dimension of the semi-discrete ordinary differential equation can be exponential large. And of course, for the optimization, so if the number of the variable is very large, then it can also be like in high dimension. So basically, like we have like many settings for all of these applications which are in high dimension. Yeah, okay, yeah, hope I have given you like sufficient like motivation of this work. That is like, why do we really care about quantum algorithms for non-unitary dynamics, and why we think like this can have like many applications. And then I will just like move on to the setup of the work and the main result. So the setup is that, so in this work, we will only consider the linear ordinary differential equation. And for now, I will just like only consider this homogeneous term. That is, I have a differential equation, and then like I have my coefficient matrix to be negative a of t. And then like for this differential equation, so basically like I'm not assuming A to be Hermitian or anti-Hermitian, so it can be in general, but I will just like decompose my coefficient matrix to be something like this. That is, I will decompose A to be L plus IH. Here, for L and H, they are both Hermitian matrices. And I want to mention that, so this is not an assumption. It is just like a decomposition for any matrix, because like we can always define my matrix L to be something like A plus A diagonal over 2, and H to be something like A minus A diagonal over 2I. So this is really not an assumption. So it is like quite general. And you can also view this as a matrix version of the decomposition of a complex number to its real part and imaginary part. Okay, so yeah, this is like the equation that we want to consider, and now we want to solve this. We want to consider the quantum algorithm. So we have to define what do we mean by like solving this equation on a quantum device. So here we just like follow like many of the works along this line, also like many of the works in solving linear system, that by solving this ODE quantumly, I'm referring to the case that I want to like prepare a quantum state encoding the solution in its amplitude. So basically like I want to like prepare the quantum state like this, and then here like all of the solution the solution, or each entry in my solution correspond to like the amplitude, and J is the computational basis. And of course, like here the evolution is not unitary, so we cannot guarantee that the final solution will also be normalized. So basically like we just want to like prepare this normalized solution. And if you just write down this definition, you can directly see that there might be some caveats in this definition. So for example, like here we only have the normalized solution. So actually like we lose a little bit of the information in my solution. That is really, we lose the norm information if we just want to only prepare this quantum state. And the bigger issue is that, so once we have this quantum state, so it is not the end, because like the differential equation is no longer a quantum dynamic. So probably it's kind of like artificial, like the output state in the HHL algorithm. So maybe we have to do some post-selection or post-processing to really get some classical information. And then like this might take some like extra cost, but here I just want to like give this caveat. And then, but like in this work, so we will still stop at this level, and then we have a quantum state input, and they want to like prepare this quantum state output. Okay, so this is like the setup of the work, and then we'll just like move down to the main result of our work. That is, so now we consider the general non-unitary dynamics. So the idea of our approach is to relate this with the Hamiltonian simulation problem. It is kind of like a standard thought in many math problems. That is, so we know how to solve some problem, and then if we want to tackle a new problem, then we want to see that whether we can reduce the new problem to the problem that we know how to solve. And then like here we just use the same idea. That is, we want to see, like, can we like relate the general non-unitary dynamics with the Hamiltonian simulation problem? And the answer is yes. And here's like the main result. That is, so basically like the relation that we found is that, so for any non-unitary dynamics, it can be represented as a linear combination of Hamiltonian simulation problem. So the main result is in this formula. And for the, let me explain this formula a little bit. That is, for the left-hand side, it is the evolution operator of my of my general ODE. So basically, like you can just view this as the time-dependent version of the evolution operator. It's basically just something like e to the negative at in the time-independent case. So the left-hand side is the evolution operator that we want, and on the right-hand side, I have a continuous linear combination of many unitaries. So basically, like it is an integral, and we have some kernel function 1 over 1 plus k squared, and we have some kind of unitary operator u of k. And for those unitary operators, they are defined through the Schrodinger equation, which is presented here in the last equation. So like for this Schrodinger equation, the Hamiltonian we have is something like KL plus H. So in front of everything, we have an imaginary unit, but like here, remember that L and H are both Hermitian matrices, and then like we just like multiply the Hermitian part L by some kind of like frequency term K, and then like so the entire term it is still like a Hermitian matrix, and then like this equation is a Schrodinger equation. So this is the theorem, and of course we have some additional assumption on the stability. That is, I'm assuming that my Hermitian part is positive semi-definite, and then actually like if you have some negative definite matrix or some indefinite matrix, then there will be some like stability issue. But that is the issue for all the quantum algorithms for differential equation. Okay, so this is the main result. It's like on the left we have some general time evolution operator. On the right we have a linear combination of many unitaries. I guess I have a question. Yes.
Just a question. Do you run in your proof like into any Lindblad condition at some point?
We don't have any further assumption on that. Yeah, it's just like this general decomposition. Okay, great. Yeah, so now I'm showing you the result, but like it's at this point it's not that intuitive. So I just want to like explain this formula a little bit. So I'm not going to like explain the detailed proof, but I really have some backup slides. So if we have time at the end, or if you are really interested in, so we can definitely discuss about the proof. But here instead, I just want to show you some. Yeah.
Would you take a question about the formula, the right-hand side? So I wonder why you call it a Hamiltonian simulation problem, because here you are integrating over all of R. And in Hamiltonian simulation, usually we integrate from like start, like 0 to t, and that's what we care about. But here the integration is a little different. Could you relate?
Oh yeah, it is because like the reason is that, so here's like we're integrating like with respect to this variable k, and for each k, so for example u of k, it is integral from 0 to t, which means that by Hamiltonian simulation, I'm meaning that, so this Hamiltonian simulation is integrating from 0 to t, and then the linear combination really means this integral over the real axis. Yeah, that's the name. That is like, yeah, for each unitary operator, so we have to like do some like further like integral or some like quantum algorithms, but like on the top of that, so we have another like linear combination, which is what we mean by linear combination of Hamiltonian simulation.
Do you have infinitely many UK?
So far, yes. But like in the implementation, I will do some discretization. I will talk about that later. Yeah, so far we have infinite many unitaries. Yeah, yeah.
This is maybe a silly question, but your assumption is L is positive semi-definite.
That's right.
But the K values can be both positive and negative, so
yeah, that's right.
why can't you just observe the sign?
Oh, it's yeah, that's a good point. It's really like yeah, I think like this like positive semi-def is kind of like a technical assumption in the proof. So I just wonder if like we have some intuition on that. I'm not sure about that at this point, but I will just like think of later. Maybe we can just discuss this offline. But like, yeah, this assumption is really, I mean, comes from the proof, and I think like in all the existing quantum ODE solvers, so they also pose this assumption, because if we don't have this assumption, so for example, if the L part has some negative eigenvalue, then like there's some possibility that the solution will blow up, and then like the cost will be exponential.
I think what you're actually doing is to do e to the minus a. If you look at the scalar version of this, the left-hand side is e to the minus x absolute value. So your observation is correct that it is symmetric, but it doesn't solve the ODE. Only when x is positive, then you are solving that ODE. When x is negative, you are solving something different.
Great. It's great. Thanks. Yeah. Okay, great. So now I will just like try to show you some intuition of this formula by considering some special cases. That is, okay, now I'm going to like restrict myself to the time independent case. So like then my evolution operator will just be e to the negative at. which is equal to e to the negative L plus IHT. And then like the right-hand side is the formula that I have. So basically like those are the unitary operators. And so the Hamiltonian will be something like KL plus H. And then now let's consider some special cases. So the first special case is the Schrödinger equation case, or the Hamiltonian simulation case. That is, if we assume that in my matrix, I only have the H part, that is, I'm assuming that L is equal to 0, then I only have IH, and then like the evolution operator will be the Schrödinger equation, and then like the LCHS formula will become something like this. So on the left-hand side, we have e to the negative IHT, which is the Schrödinger equation, and on the right-hand side, so since like in the original formula, so we only have k in front of this L part. So here, if we make L to be 0, then like we do not have the k part in my unitary operator. Basically means that here we only have a single unitary operator, even on the right-hand side. So this integral becomes like a trivial integral. So it's just like an integral over this kernel function over a scalar valued function. And the proof for this formula is trivial because we know that. So for this kernel function, 1 over 1 plus k squared is a probability distribution function of the Cauchy distribution. So the integral over the entire real axis will definitely be 1. Okay, yeah, this is like the trivial special case. And now we move on to a little bit non-trivial case. That is, if we only have the Hermitian part. That is, I'm assuming my H to be 0, and I only have L. So this corresponds to the invariant time evolution, or some like heat equation or something like that. So basically, like we won't have like this e to the LT, and then my LCH formula becomes something like this. That is, on the left-hand side, I have e to the negative LT. On the right-hand side, so now I have like infinitely many unitary operators. So because like here I have a k in my unitary operator, and then like so the formula will look like this. But if you're familiar with the Fourier transform of the exponential function, then like this is nothing beyond the Fourier transform, or the matrix value Fourier transform, because like if we compute the Fourier transform of this exponential function e to the negative absolute s, and then the corresponding result will be exactly this Cauchy-Lorenzi distribution 1 over 1 plus k squared. So this is like the Fourier transform formula, and then since by the Fourier transform we have some additional I and k inside my exponential on the right-hand side. Yeah, this is like so basically like the proof is really just based on Fourier transform. And these are the two special cases. So actually, like when I mentioned that, so it is kind of surprising that, so even for the general case, similar formula still holds. So actually, like when we found this formula, we kind of like surprised about like actually we can have both Hermitian and anti-Hermitian part at the same time. And then like the proof, I want to say that it is kind of like beyond the Fourier transform or something like that. So basically, we use some techniques in complex analysis to show the general proof. But like I always think like it is always good to like start from the special cases, and then like I want to show you that so okay, it can be generalized to the most general case with both Hermitian part and anti-Hermitian part. Okay, so like yeah, this is like kind of like the intuition of the behind this LCH formula, and now we have the formula. So we still don't have an algorithm, have a quantum algorithm for this. And next, I will just like discuss how we can design a quantum algorithm based on this formula. Okay, any questions so far? Or okay, great. So yeah, for the algorithm, so now of course, if we want to implement this, then we have to make this to be like something like a finite sum. So infinite sum, we don't really know how to deal with that. And then like the idea is that so we'll first like do some numerical quadrature. So basically, like you can just do like whatever quadrature you want. So it is quite flexible. So for example, like I can just like truncate this and the integral over the entire real axis by some like finite interval. And on the finite interval, I can apply maybe Gaussian quadrature, or maybe even more simpler like the trapezoidal rule, or maybe just like the Riemann sum formula. Then like after that, what we will get is that it will become something like a finite sum of finitely many unitary operators. So I will have a formula on the right-hand side, and then this becomes the problem of linear combination of unitaries, right? It's exactly the linear combination of unitary, and especially it's the discrete version of the combination. And then we only need to implement the right-hand side, this summation of C times U. And to do this, actually, we also have some like flexibility. That is, so we can do this quantumly, or we can do this in a hybrid fashion. So for example, so this is just like a linear combination of unitary, then we can, of course, use the quantum subroutine with the same name, linear combination of unitaries, or LCU. So basically, it was first proposed by Childs and Wiebe for Hamiltonian simulation problem, but it turns out to be a very powerful tool for designing quantum algorithms beyond that. And of course, if we don't like a purely, quantum approach, we can also try to do some hybrid approach. So this is based on the importance sampling. That is, I think you've already heard that in the previous talk in this workshop, but I will also mention this later. Yeah.
So for the unitary UK, for K negative, the spectrum is unbounded from below because K is negative and L is positive semi-definite.
Oh, in that case, so if K is negative, that doesn't matter because the dynamics will be a unitary, right? For the unitary dynamics, it is reversible. So we can just go forward or go backward. And then if K is negative, then that will still be fine.
So this discretization still you keep the positive part only?
No, we will include both positive part and negative part. Yeah, it is kind of we truncate this real excess into maybe negative K to positive K, and then we will also keep the negative part. But it doesn't affect the efficiency for unitary operators because here we have the Hamiltonian simulation operators, and then we in the Hamiltonian simulation algorithm, so actually we don't have any restriction on the signs of the matrix or the eigenvalues, so on and so forth, because it is a reversible dynamics. Yeah.
What does the bound on the error in this truncation look like?
I will discuss this later. Yeah. Okay, great. So yeah, here's the high-level algorithm for this LCHS formula, and then now I will just discuss these two specific approaches. So for example, in the quantum approach, so it is the LCU. So I think many of you are familiar with this approach, but I just want to still quickly give you this one-page introduction of the LCU. That is so the LCU is kind of a general framework of computing the linear combination of many unitaries. So I would always like to start with this toy model. That is, so for example, if we consider computing the uniform combination of just two unitaries, I just want to compute the average of U0 plus U1, then basically we can use the circuit like this. That is, I can add one more ancilla qubit, and then what I'm going to do is that I'm going to start with the ancilla qubit and then apply a Harman gate here. And after applying the Harman gate, so the state I have is something like this. That is, I have some uniform superposition in my ancilla qubit, and I have in the system register, I have my input state. And after that, I will apply the key part of the LCU algorithm, which is the controlled operation of the unitaries. That is, I'm applying the controlled version of U0. The control really means that if the value in my ancilla register is 0, then I will apply U0. But if the value in my ancilla register is 1, then I will apply U1. So basically, these are the controlled application of the unitaries. And what I will have is something like this after the controlled unitary. So basically, we have, for corresponding to the 0 part, we will have U0 acting on my initial state. And for the 1 part, we will have U1 acting on my initial state. After that, I will apply another Harman gate in the ancilla qubit. And what I will get is something like this. So it's just some straightforward linear algebra calculation. But the interesting thing is that, so if we look at the first part, the part corresponding to the 0 value in the ancilla qubit, so the remaining part is exactly what we want. That is the average of U0 and U1. So, but since you know that the average of U0 and U1 is definitely, it is not a unitary operator. So we have some junk state. We have some orthogonal state which corresponds to the ancilla with 1. And the last step is we do some measurement. That is we measure the ancilla qubits. So if the value is 0, then we succeed. And then in the remaining part, we will get the state that we want, of course, the normalized state. But if we fail, then we just redo this circuit until a success. So basically, we will have some overhead due to the repeat or the success probability. So this is the toy example. And actually, the general LCU is, it's quite similar. That is for the general LCU. So basically, we would replace this Hammond gate by something called the prepare oracle, which is the state preparation oracle corresponding to the coefficients that I want to compute, or the coefficients related to the linear combination of unitary. So if you look at the toy example, so in the toy example, I only have 2 coefficients, and both of them are equal to 1 or something like 1/2. So basically, like the Hammond gate will serve as the prepare oracle in the general case. And in the middle, I have some controlled version of the unitary, so which is called the select oracle in the LCU, so but they are just like some controlled version of the unitary, which means that basically the LCU approach can really be generalized to like multiple unitaries with arbitrary coefficients. Suppose that we are given all of these oracles. Yeah?
So the number of ancillas that you need to introduce are the number of J's you have?
It is the number of the ancilla will be log J, because like here actually like if we have the efficient state preparation oracle, then it will be log J. Yeah. Okay, great. Yeah, this is like the quantum approach. And of course, like in the quantum approach, you can see that so basically LCU is very powerful, but we need some ancilla qubits, and we need some controlled application of the unitary, and also we need like some oracles, so maybe it is not quite, I mean, in the early fault-tolerant regime, so if we just want to like make this to be more, a little bit more near term, then probably we just want to consider the hybrid implementation. So the hybrid implementation is really based on the importance sampling that is, so for example, like, so here we start with our LCH, the discretized version of the LCHS formula, so we have the final solution to be some linear combination of unitaries acting on my input state. And then suppose that I'm interested in the observable, something like U dagger times O times U. And then we can just use this linear combination. We can compute that, OK, it is like something like a linear combination of many observables. And then what we are going to do is that, so since here's just the linear combination of observables, so basically like we can just do the importance sampling. And that is, if the coefficients is large, then we will just like sample it with high probability and do the computation, and then like give this kind of part more weight. And if the coefficients is smaller, then we'll just have some low probability of sampling that. So basically like the approach is the standard approach. That is, we sample my index according to the probability proportional to my coefficients, Cj times Cj dagger. And I forgot to mention that, so in my application, all of the coefficients C are real numbers, so basically you don't really worry about the complex number here. And after the sample, so for each sample, this sample strategy is on a classical device, and then like I will just use my quantum device to compute the corresponding observable, like corresponding to like each sample of my index. And after that, I will just like average all the observables, and then it will be this output random variable will be a good approximation of the desired observable that I want. Yeah, this is like the hybrid implementation. So basically, like it's still like based on LCU, but like we just like want to make this to be like in the hybrid, and then like to be a more like use like few like ancilla qubits and less uncontrolled logic. Yeah.
What do you need discretization if you implement this one?
Sorry, what the discrete?
Why do you need to discretize the?
Oh, actually, like we don't really need to discretize this, of course. Yeah, for the integral, we can also do like directly do this. Yeah, yeah. Yeah.
So the thing you want to measure you would implement is like a controlled U, controlled O, controlled U. Yes.
Actually, in the hybrid implementation, we don't need a controlled version, right? Yeah, because like here, like we suppose that we have the value of the sample, so basically like we can just like, of course, like for each circuit, they will be different, but they are not in the controlled version. So they will be different according to the specific value of my Kj and Kj prime, but like actually like we don't have the controlled version. Yeah, because like they are not like implemented in a coherent fashion. So basically like we just like run the circuit again and again for each circuit, so they might be different, but yeah, it's just like it's the standard version of the unitary.
I think what you actually said is that even for Harman test.
Oh yeah. For sorry. Yeah. For the Harman test, we still need like a controller. Yeah.
I thought I hadn't had enough coffee. Okay, so in a lot of cases when you have overlaps like this, you can remove some of the controls by canceling out some of the time evolution. Mm-hmm. Does that work here, or because your Ks are different, it doesn't work anymore?
If K is different, I think it probably does not work. Yeah. Okay. Great, yeah, this is like the implementation. So I have like completed like the majority of the talk, and then like next I will just like discuss some generalization of our approach and the comparison with the existing algorithm. So far we only focus on the homogeneous case. That is, we only have this negative A times U. But now actually like our approach can be directly generalized to the inhomogeneous case with the presence of this source term B of t. So the idea is quite simple. That is, we use so-called the Duhamel's principle. So the Duhamel's principle is basically like we just represent the solution of the general inhomogeneous ODE by the evolution operator of the homogeneous ODE. So if you look at the formula right here, so in the first term, we have the homogeneous solution corresponding to the homogeneous ODE. And on the right-hand side, so I'm missing some kind of like ds here. So yeah, on the right-hand side, so basically like we have an integral that is like we have the evolution operator from S to t and then acting on my inhomogeneous case. So here's like kind of like, of course, like there are some like technical proof for this formula, but like intuitively, so basically like it can be represented this kind of form that is like, so we have some homogeneous solution, and then those B term will add some perturbation in my derivative. So if the perturbation happens at the very beginning, then it will be propagated by my homogeneous solution, which means that so if we have some B of S, then I will have like this homogeneous propagation operator starting from S to t, and then like I should like really sum up all of this term and then contribute to the final solution. So this is kind of like an intuitive explanation of the Duhamel's principle. But generally, so we have this formula, and we can see that so the implementation is quite straightforward because now we know how to do this homogeneous case. So for the homogeneous case, it's just the LCU. And for the second part, so here we only have the homogeneous evolution operator, so it is still the LCU. And then we have another integral, which means that it is just like another layer of the linear combination on top of everything. So basically like here for the inhomogeneous term, we only need to do a linear combination of Hamiltonian simulation. So we just have like another layer of the linear combination, and then like we will have a quantum algorithm for the inhomogeneous case as well. Yeah, okay, this is like the generalization, and then now I'm going to like compare our method with the several like existing quantum algorithms for differential equation. So the first comparison I want to make is the comparison with the quantum singular value transformation, or QSVT. So it is like a really powerful approach for performing a general matrix function. But as its name suggests, so the QSVT is really performing some singular value transformation. But we know that for the differential equation operator, so if you imagine we only have a time-independent matrix A, and for example, I'm assuming A is diagonalizable, then actually like for the differential equation, we are doing the eigenvalue transformation. So basically, if we want to like apply the QSVT technique to the ODE, then we have to make sure that there should be some relation between the eigenvalue transformation and singular value transformation, and we know that it is not the case in general. So for example, like if our matrix is only Hermitian or anti-Hermitian, then for example, if we think of the Hermitian matrix, then the eigenvalue and the singular value transformation, they are like very similar. So basically, like we can just use the QSVT, and we can. This is also true for the anti-Hermitian matrix. However, if we go beyond this case, that is, we only have Hermitian or anti-Hermitian, so we have both Hermitian and anti-Hermitian, or if we even go beyond the time-independent case, maybe we consider the time-dependent case. And at this point, so it is not quite clear how we can use the quantum singular value transformation technique to perform this differential equation operator. But our LCHS formula can be applied to the most general case. So this is like a comparison. And of course, I want to mention that this is, so far, it is still like only for the differential equation operator, but like QSVT can do something more general in the Hermitian case. Okay, so this is like the first comparison. And the second comparison I want to really make is the comparison with many existing differential equation algorithm. So, but before that, I want to like briefly go through this. I think like probably like Dee will like talk more on this like in the afternoon session. But I want to like give like a little bit like preview of this thing that is like for many existing quantum algorithms for ODE. So basically, they kind of like based on the general approach that is, for example, like they first do some time discretization, and after time discretization, they will like for example, here I'm just using my simplest forward Euler. And after that, I will just transfer this differential equation into a large linear system. And for the large linear system, it is a solution for so-called the history state, or the entire trajectory of my dynamics. I've just like considered a solution of U0, UH, U2H, all the way to UT, where H is my time step size. And then since my original differential equation is linear, then the entire thing is still like a linear evolution, still like a linear system. Then I can apply my favorite quantum linear system algorithms, so for example, like the HHL algorithm and many like advanced ones. And then like I get the solution, and if I only want the final solution, then probably I need to do some post-selection. This is the general approach, and of course, like there are many different types of the algorithms. So, but like the difference is really how we can do this time discretization and how we can like apply this quantum linear system algorithm. So we can use some high order discretization to make the entire algorithm to be high order. So this is a really, powerful approach, but it has its own computational overhead. So the overhead is really the high state preparation cost. What do we mean by high state preparation cost? Because like here, I'm transferring the original differential equation to a large linear system. And in the linear system algorithm, actually, we need multiple copies of the right-hand side. So the reason is really because like even for the linear system problem, it is not a unitary problem. So we have some like post-selection, post-processing, and then like we really need to like run the entire algorithm again and again, and then also like we have some kind of like applications inside the algorithm. So basically like in this approach, we need multiple copies of the right-hand side, and especially multiple copies of this U0. However, this is quite natural for Schrodinger equation, right? Because if you think of the Hamiltonian simulation algorithm, so for the Hamiltonian simulation algorithm, so probably I can just like go to this slide. That is, for the Hamiltonian simulation algorithm, actually, we will only start with a single copy of my input state, right? With a single copy of the input state, I sequentially apply my local evolution operator, U0, U1, U2, all the way to my final operator, and then I will just get my final solution. So in the approach for Hamiltonian simulation, actually, we only need a single copy of the input state. But if we consider this general approach, then actually we really need multiple copies of the right-hand side. And it can be costly if the initial state preparation, the initial state preparation oracle is very expensive. And if you think of our approach using linear combination of Hamiltonian simulation, right? Since we relate our equation with the Hamiltonian simulation problem, so basically it really means that we can take advantage of the good part of the Hamiltonian simulation, which means that we can reduce the number of the input states that we need. And here's like a comparison. That is like, so here I'm comparing our linear combination of Hamiltonian simulation algorithm with the probably like the state-of-the-art linear system-based quantum differential equation solver, which is the truncated Dyson series method. And then like here on the query complexity, if we look at the number of the queries, the initial state, then in our method, so we only have a linear dependency in terms of Q, where Q is something like the norm decay rate in my solution. So we only have this kind of, we only require like this number of the input state or the oracle for the initial state. However, if we look at the truncated Dyson, so the state preparation cost will be very high. So it has this parameter Q. Actually, technically, it will be another parameter Q, which is even larger than this standard Q. And it involves some other parameters, for example, this alpha, which is the spectral norm of my coefficient matrix, and it will also have some time dependence and some dependence on the precision. So we have some like extra like parameter. But in our algorithm, actually, like we avoid all the explicit dependence in terms of the spectral norm, the time, and the precision in the state preparation oracle. And I will also mention that. So here we still need multiple copy of the unit of the initial states due to some like measurement, but like actually we cannot do better because like we can really prove that the lower bound is also like linear in terms of Q. So basically like our approach has already achieved the optimal scaling in terms of the state preparation. However, if you really look at this table, actually you can find some like drawback of our algorithm. That is, if you look at the query complexity in terms of the matrix, then actually like our method is worse than the truncated Dyson. It's really, for example, here we have a 1/epsilon scaling, but in the truncated Dyson it is only like log 1 over a polylog 1/epsilon, which indicates that our method is actually a first order method. So it is not a high order method. And this is really because of the discretization of my integral, the truncation error. So why? Because so here, let's go back to the continuous version of the linear combination of Hamiltonian simulation formula. So since in our equation we have to do some discretization of this integral. So what we'll do is we will truncate this into a finite interval. But here comes the problem. If we do the truncation, the number of the k should be very, very large, because here we have the kernel function to be a quadratically decaying function. So if we want to control the truncation error by some epsilon, then we have to make the truncation order to be something like 1 over epsilon to control to bound the tail probability by epsilon. So this is really because I have a quadratically decaying kernel function, and this will result in, for accurate simulation, this will result in a very large value of k. And since my k is the frequency term and it will enter the Hamiltonian in my unitary, so we will have a very, very large Hamiltonian spectral norm. And then the next step, I will apply my Hamiltonian simulation algorithm. And for many Hamiltonian simulation algorithms, they typically scale linear in terms of the spectral norm of the Hamiltonian, which means that I will have a high cost in terms of the matrix order cost. So this is really the reason. That is we have some slow decaying kernel, and then we need to apply the Hamiltonian simulation algorithm. So, and then now we want to really further improve this formula. That is we want to get rid of this drawback. So actually we have two solutions. So it's really because on the right here's the logic of why this drawback is happening. And what we can do is that we just cut one of the steps. That is, so for example, if we cut here, then we can try to design some better kernel function, right? If my kernel function is better, then I do not need a large value of k, and then I can achieve some high order convergence. And this is one of our ongoing work, so I don't have time to talk about that today, but I would be happy to discuss this offline. And another solution is that, so how about we just try to improve this Hamiltonian simulation algorithm? That is, even if we have a very large k, but if my Hamiltonian simulation algorithm can be implemented independent of k, of course, that is not possible for generic case, but for some specific case, if we can do that, then we can also get rid of this k dependence and also make our method to be high order. And this is something that I'm going to like show you in this page, so which is exactly the interaction picture Hamiltonian simulation. So the interaction picture Hamiltonian simulation is like, yeah, sorry, it might be a little bit over time, but like, let me try to, okay, yeah. Okay, so it is kind of like, yeah, we consider the special case where L is time independent, and I'm assuming that my L is so-called fast-forwardable. And here, this is not quite efficient because like here I have a very large value k, and then my spectral norm of the Hamiltonian is very large, which means that my solution of the Schrödinger equation is oscillating very fast. The oscillating is really due to this k times L. But in the interaction picture Hamiltonian, what we will do is that we will rotate this unitary operator according to the frequency. That is, I'm rotating my unitary operator according to this e to the I k L t. And you can really imagine that if we do this rotation, then I kind of resolve all the oscillations before the simulation, right? Because like the fast oscillation really comes from this large value of k, and then I've already like resolved all the oscillation. And then the resulting interaction picture Hamiltonian simulation will be something like this, and it is independent of k, which means that we can simulate this unitary instead of the original one and to get some algorithm which is independent or only have like some weak dependence in terms of k. However, you can like realize that this is not true for the generic case because we need to know how to do this rotation efficiently. Because like for this rotation, it's just like another Hamiltonian simulation with a fast oscillation. And then what we assume is so-called that L is so-called fast-forwardable. So for example, if L is just like some diagonal matrix, then this operator is just like some controlled rotation, which can be independent of k. But in general, by fast-forwardable, I'm really meaning that, so okay, yeah, my Hamiltonian simulation here, e to the I k L t, can be implemented independent of k and of course of t. And there are some applications of this kind of fast-forwardable Hamiltonian. So, and with this interaction picture Hamiltonian simulation, we really get rid of this, this worse scaling due to the large k. And actually, the overall complexity can be linear, can be like optimal in terms of the initial state preparation oracle, and also can be a polylog in terms of the precision for the queries to the Hamiltonians or to the matrices, which means that this is like a high-order convergence method. Yeah. Okay, yeah, here's my last slides for this talk, and the summary that is like in today's talk. I discussed like a linear combination of Hamiltonian approach. We focused on the non-unitary dynamics, and the idea is that we relate our non-unitary dynamics with the Hamiltonian simulation problem by its linear combination. And then we propose a LCHS formula, and we discussed the implementation. It can be implemented by quantum LCU approach or in a hybrid fashion. And our method can achieve optimal state preparation oracle. And we discussed the drawback that is the linear convergence in terms of the matrix SS, but this can be overcome by the interaction picture Hamiltonian simulation, as well as some ongoing work on designing some better kernel function. And at the final, I also like mention a related approach that is because like the idea of relating the non-unitary dynamics and the Schrodinger equation is quite natural. So actually like there's like a equivalent formalism of our LCHS formula, which is called the Schrodingerization by Jin Liu and Yu in this paper. So it is also like a very interesting paper. So if you're interested, I'm encouraging you to also check out this formula again. And here's our work. And with that, I would like to conclude and thank you for your attention.